Okay, so welcome to section 9.6, which is Gaussian elimination. Gaussian elimination. Okay, so let's recall. Solving the system by elimination, which was my favorite way. By elimination. If we were given, say, ax plus by is equal to h, and cx plus dy is equal to k, we would multiply the first equation through. If we wanted to, say, eliminate x, we would multiply the first equation through by c, and the second equation through by a. And this would give us the system of equations a cx plus b cy is equal to ch, and then a cx plus a dy is equals to a k. And then we would subtract in order to eliminate x. So we would get something like quantity BC minus AD all times y is equal to CH minus AK, etc. So notice step 1, multiplied let's say first equation by a. Let me move this down a line. So we multiplied the first equation through by a. We multiplied the second equation through. Second equation through. By, we multiplied the first equation by c, not a, and second equation through by a. Then what do? Then we subtracted second equation from first. And all of these are valid steps. And if you understand that these are valid steps, then you will understand what we're doing in this section, because it's similar. In fact, it is elimination, but just done in a different manner with matrices. So here we go. Definition. Okay, so the augmented matrix. So the augmented matrix representation of a system of equations. So representation of a system of equations has the coefficients of x, has the coefficients of x in the first column, the coefficients of y in the second, of y in the second column, a vertical line to indicate equality, this is the augment, and the constants in the last column Okay, so i.e. that is id est, if we have the system ax plus by is equal to h, and cx plus dy is equal to k. This is equivalent to, meaning they're both equivalent. This is equivalent to having the coefficients of a in the first, the coefficients of x in the first column, namely a and c. Then the coefficients of y in the second column, which is b and d. Then the augment, which is a vertical line that indicates equality, and the constant coefficients h and k in the last column. Autocorrect will be the bane of my existence. Okay, there we go. Okay, so now let's do an example. So for example, let's see if we can extend this to 3 dimensions. So express the following. So express the following. Systems as augmented matrices. Okay, so number 1, let's say we have the 2 by 2 system. That's a terrible curly bracket. Let's say we have 2x minus 3y is equal to 5, and 4x plus y is equal to 9. Okay, so let's color code this. Let's do 2 and 4 as the coefficients of x, then minus 3 and 1 as the coefficients of y, and then 5 and 9 as our constant coefficients. So I claim that this is equivalent to the system of equations, or the augmented matrix, 2 and 4 for the x coefficients, negative 3 and 1 for the y coefficients, a vertical line for the equal sign, and then 5 and 9 for the constant coefficients, the last column line. Why is that not autocorrecting? There we go. Okay, so that's number 1. Okay, so number 2. Let's do another 2 by 2. Let's say we have x minus y is equal to 0 and 11y is equal to 22. Actually, let me move that down 1 line. Okay, so once again, let's rewrite this. I claim that this is 1 and 0 times x. And then negative 1 and positive 11 times y is equal to constants of 0 and 22. So I claim that this is equivalent to the augmented matrix whose first column is 1 and 0, whose second column is negative 1 and 11. Then we have a vertical line for the equal signs, and whose constants, or last column, is 0 and 22. So that is the augmented matrix representation of that system. Okay, why this? Okay, so number 3. Let's say we have x minus y plus 3z is equal to 4. 2x plus y minus z is equal to 5. And negative 2y plus 9z is equal to 7. Okay, so rewriting this, I claim that my coefficients of x are 1, 2, and 0 for x. My coefficients of y are negative 1, positive 1, and negative 2. My coefficients of z are going to be, what color should I use? I guess I can use green. Positive 3, negative 1, positive 9 times z. Equal to 4, 5, and 7. So I claim that the equivalent augmented matrix will be, first column are the coefficients of x, 1, 2, and 0. Second column is the coefficients of y, negative 1, 1, and negative 2. Third column will be the coefficients of z, 3, negative 1, and 9. Then we do an augment or vertical line to indicate the equal signs. My constants are 4, 5, and 7. Then I can finish my matrix. So this is the augmented matrix representation of the system. So hopefully that makes sense how to draw that. Okay, so now let's do elementary row operations. And this has to do with what I did in the recall. Elementary row operations. Okay, so number 1. Any row of a matrix, may be multiplied by a non-zero constant. And that we annotate by k times row I. So if we go back to my recall, I multiplied by C and by A, the first row and the second row, respectively. So we know that that's allowable. Number 2, any 2 rows of a matrix, or any 2 rows of a matrix, rows, not columns, rows of a matrix may be interchanged, So the way we annotate this is row I goes to row J and vice versa. Okay, so do you agree that it doesn't matter which equation is written first in a system, as long as we have all 3 equations? So that's what they mean by any 2 rows may be interchanged, because each row indicates 1 equation. And last but not least, number 3, the entries in any row, may be added. And by added, I mean also subtracted, added to the corresponding entries. Entries in any other row. So we call this row I plus or minus row J. And that, do you agree that I subtracted 1 row from the other? And we're allowed to do that within matrices, though it's going to be a little bit different. So let me show by example in a moment. Okay, so for example, So put the following systems in an augmented matrix. So put, or how about this, express the following systems with an augmented matrix, It's terrible, augmented. You know what, I'm just going to hyphenate. I'm not sure where to hyphenate. Matrix. And then perform. The indicated row operations. Okay, so number 1, we have 2x minus 3y is equal to 1, and 5x plus y is equal to 11. Then I want you to find, how do I want to put this? 5, row 1. Then let's do negative 2, row 2. Then let's do row 2 plus row 1. Then let's do negative 1/17, row 2. And then 1/5, row 1. So let's do all of that after we put this in an augmented matrix. Okay, so I'm just going to go ahead and do the augmented matrix right away. I claim that the coefficients of x are 2 and 5. The coefficients of y are negative 3 and 1. Augment the constant coefficients are 1 and 11. Okay, so let me show you how we do this. So I'm going to do an arrow to the right. The first step is 5 row 1. 5 row 1. So what I do is I multiply each entry in row 1. Come on, why does this not autocorrect? By 5. So this will be 5 times 2. This will be 5 times minus 3. Augment. This will be 5 times 1. And the row 2 stays the same. 5. Actually, do you know what? I could do 2 operations at once, so let me do that. Let's do negative 2 row 2. Maybe in a different color, maybe like orange. Negative 2 row 2. Since they're not, sorry, row 2. So let's do negative 2 times 5. Let's do negative 2 times 1. Then let's do negative 2 times 11. So I claim what we get then will be the augmented matrix, whose first column is, actually, yeah, maybe I should put that over here. So this is going to be, what do we get? First column will be 10 and negative 10. Next column will be negative 15 and negative 2. We'll have our augment. And then we'll have 5 and negative 22. So that's what happens there. Okay, so now the next step I want to do, actually let me move this so they're aligned. Let's go ahead and do row 2 plus row 1. So if I have row 2 plus row 1, what that means is that I'm changing the first row mentioned. And the first row mentioned here is row 2. So row 1 is going to stay the same. But row 2, which is now negative 10, we're going to add row 1, which is 10. So row 2, which is negative 2, we're going to add row 1, which is going to be minus 15, because we're adding a negative, which is subtraction. We don't want to put plus minus. We are, after all, in pre-calculus. Okay, now we have negative 2 plus row 1, which is 5. Okay, so row 1 is just going to remain the same. Row 2 was listed first, so row 1 is just 10, negative 15, and 5. Okay, so what does that give us? Okay, so that gives us 10 and 0, negative 15 and negative 17, augment, 5 and negative 17. Which is interesting because the next step is negative 1/17 row 2. So negative 1/17 row 2. That means I'm going to multiply each entry in row 2 by a negative 1/17. So I'll have a negative 1/17 times 0. I'll have a negative 1/17 times negative 17. Augment. Oh, come on, autocorrect. Oh, really? Come on. Then I will have a negative 1/17 times negative 17. And row 1 just stays the same. It is 10, negative 15, and 5. Okay, so what does that give us? That gives us then 10 and 0, negative 15 and 1, augment 5 and 1. Okay, so what's the next step? The next step is to do 1/5 of row 1. Okay, so 1/5 of row 1. Okay, so we have 1/5 times 10. We have 1/5. 1/5 times negative 15. Augment. We have 1/5 times 5. But the second row just stays at 0, 1, and 1. Okay, so when all is said and done, what do we get? We get 2, 0, negative 3, 1, augment, 1, 1. So let's note something. So that's all I asked you to do, but note something. If I take this, let's make it green. This is actually equivalent to the system. 2x minus 3y is equal to 1, and y is equal to 1, which is much easier to solve than the original system. Okay? We're not there yet, but I just wanted you to note that. Okay, so let's do number 2. So let's say we have x plus y is equal to 5 and x minus y is equal to 1. Then I want you to evaluate row 2 minus row 1, then negative 1/2 row 2, then row 1 minus row 2, and just those 3. Okay, so let's begin. The coefficients of x are 1 and 1. The coefficients of y are 1 and negative 1. Augment for the equals, and 5 and 1. So the first thing we want to do is row 2 minus row 1. Okay, that means row 2 is changing because it's written first. So I'm going to have row 2, which is 1, minus the corresponding entry in row 1, which is 1. Then I'll have negative 1 minus 1, augment. Then we'll have 1 minus 5. Now row 1 just stays the same. It's 1, 1, 5. So what this gives us then is 1, 0, 1, negative 2, augment, 5, negative 4. Okay, so now I'm going to do negative 1/2 row 2. So row 2 is changing, so I'm going to have negative 1/2 times 0. I will have negative 1/2 times negative 2, augment. I will have -1/2 times -1. And row 1 just stays the same, which is row 1 is 1, 1, and 5. So what do we get then? We get 1 and 0. We get 1 and 1. Augment. We get 5 and 2. So now we want to do row 1 minus row 2. So now row 1 is changing, row 2 will stay the same. So row 1 is 1 minus 0, then 1 minus 1, augment, 5 minus 2, and row 2 is still 0, 1, 2. So what this gives us in the end will be the system 1, 0, 0, 1, augment, 3, 2, and if you note, that actually gives us x equals to 3, y equals to 2, and we're done with that one. Not that you had to do that last part, but it's interesting to note it. Okay, so hopefully that's making sense. Elementary row operations. Okay, so definition. So Gaussian elimination, that's what the title of this section is. So Gaussian elimination is the method of solving linear systems. So is the method of solving linear systems. Linear systems by way of elementary row operations. By way of elementary row operations. So basically what we've done above. So there's some terminology. How do I want to do this? Let's do this in purple, I guess. So terminology. So a matrix of the form. A matrix of the form. Let's say it looks something like A, B, C, augment. I'll do it for 3x3s, but it's analogous for 2x2s. Then 0, 0, and D, E, K, then 0, 1, and M. So if you have this form, this is in row echelon form. So a matrix that has zeros underneath the diagonal So let me show what the diagonal is here. So underneath this diagonal here, if there's zeros, then that's row echelon form. However, if we end up with something like so, 1, 0, 0, 0, 1, 0, 0, 0, 1, augment, x, y, z. This is in reduced row echelon form. Reduced row echelon form. Okay, so where have we seen both of these before? Notice that up here, this is row echelon form. We've got a 1 here and zeros beneath the diagonal. Whereas over here, we've got 1s along the main diagonal and zeros everywhere else. So let's note something about the reduced row echelon form. It solved the equation for us, right? So note. Reduced row echelon form. Reduced row echelon form solves the system. And I should say it solves the system that does have a solution. Okay, so how do we solve systems? So solving systems using Gaussian elimination. Maybe I want to do this with this color. Solving systems, and I'm just going to color code this using Gaussian elimination. I will try. It's easier for me not to use too many words for this. So let's go ahead and have a 3x3 for illustration. So A, B, C, and an augment. Then D, E, F, G, H, I. Then let's do M, N, and T. Okay, so step 1. We want A to go to 1. That's our goal. Okay. Step 2, which I could have done this in, let me do that. What I'm going to do is make this dashed. Nope, it's not auto-correcting for me anymore. There we go. Okay, so step 2, I want that D and G both go to 0. Then step 3, E to go to 1. Then the next step, so step 4, I want B and H to go to 0. Step 5, we want I to go to 1. And finally, step 6, we want C and F to go to 0. So that's a process of Gaussian elimination, and we do these using, so by way of elementary row operations. Okay, so let's solve some systems using this. So notice my goal is to get 1s across the main diagonal, starting at the leftmost column, get the 1, then 0 everything out. Then the second column, get the 1 in the middle, 0 everything else out. Then the third column, get the 1 on the bottom, 0 everything out. So that's the overall goal, if possible. So for example, so let's solve the following systems using Gaussian elimination. So solve the following systems. And when I use the term solve here, the only way to solve by way of Gaussian elimination is to put it in reduced row echelon form, because that solves the system. So solve the following systems using Gaussian elimination. Okay, so number 1, let's say we have 2x minus 3y is equal to 0, and x plus 4y is equal to 11. Okay, so once again we start with our augmented matrix. Coefficients of x are 2 and 1. Coefficients of y are negative 3 and 4. Then augment for the equal sign. Constant coefficients are 0 and 11. Bracket. So my first goal is to get a 1 where this 2 is, right? So step 1 is to make this 2 a 1. So to that end, I'm going to say row 1 minus row 2, because that'll get me a 1 in that place. Because 2 minus 1, negative 3 minus 4, augment, 0 minus 11. Second row is just 1, 1, 4, and 11. So this gives us a system. 1, 1, negative 7, 4, augment, negative 11, and 11. Okay, so the next step is to get, oh, did I do the color coding wrong? Yes, of course, that was supposed to be blue. Okay, so the next step is to get this guy right here to go to 0. Right? So to that end, I claim that row 2, row 2 minus row 1 will get me that 0. Because 1 minus 1 is 0. Then 4 minus a negative 7 is plus 7. Oh, sorry, that should have been minus a negative 7 is plus 7. Augment. Then we have 11 minus a negative 11. And row 1 is still 1, negative 7, negative 11. Okay. So we get 1 and a 0, so column 1 is taken care of. Then we get negative 7 and 11. Augment. We get negative 11 and 22. So my next step is to get a 1 in the next, along the diagonal. I want that to be a 1. So I claim that if I do 1, let's do this. If I divide by 11, so 1/11th, row 2, that'll get me the 1 in that place. So I'm going to do 1/11th of each entry in row 2. 1/11th times 0, 1/11th times 11, and 1/11th times 22. Row 1 is still 1, negative 7, negative 11. Okay, so what that gives us then is 1 and 0, negative 7 and 1, and negative 11 and 2. Okay, so we've got the 1. Now my goal is to get a 0 where this negative 7 is. Oh, wow, okay, that was weird. Okay, so if I add 7 to that, that would give me to 0. So I need to somehow add 7. So to row 1, I need to add 7, but I can't just add 7 willy-nilly. That's not a row operation. But I can add 7 times row 2. Let me show you. So to row 1, I'm going to add 7 times row 2. So 7 times 0. To row 1, so negative 7. I'm going to add 7 times the entry in row 2, which is 1. Augment. To row 1, I'm going to add 7 times the corresponding entry in row 2. And row 2 is just 0, 1, and 2. So what this gets me then will be 1 plus 0 is 1, 0. Negative 7 plus 7 is 0, 1. Augment. Negative 11 plus 14 is 3, and 2. So I've solved the system. So the system is 1 times x is equal to 3, and 1 times y is equal to 2. So we have the point 3, 2 is the solution, the point in the plane where these two lines intersect. So we want to note something very important. So warning, caveat, warning. Cannot subtract a constant. So I couldn't just add 7, I had to add 7 times row 2. That's the only time I'm allowed to add. We can add corresponding rows, we cannot just add constants willy-nilly. Okay, so what number was that? Number 1, I believe. So let's do number 2. So let's say we have the system, let's do a 3 by 3. X plus y minus z is equal to 1. X minus y plus z, it's a terrible z, is equal to 1. Let's do x plus y plus z is equal to 3. Okay, so now this is a 3 by 3. The coefficients of x are 1, 1, and 1. Coefficients of y are 1, -1, and 1. Coefficients of z are -1, 1, and 1. Augment for the equal signs, then 1, 1, and 3 for my constants. Okay, so the first step is to get a 1 here. Check mark. Okay, so the second step is to get zeros here. Okay, so to that end, I claim that if I have row 2 and row 3 each minus row 1, that'll get me what I'm going for. So row 2, 1 minus row 1, -1 minus row 1, 1 minus row 1, so plus 1, augment 1 minus row 1. Now row 3 is going to be 1 minus row 1, 1 minus row 1, 1 minus a negative, so plus 1, row 1, and 3 minus row 1, where row 1 just is the same. So namely 1, 1, -1, 1. Okay, so what do we get? We get 1, 0, 0. Then we get 1, -2, 0. Then we get -1, 2, 2. Augment. 1, 0, 2. Okay, so my next step is to get a 1 in this position. So to that end, I'm just going to go ahead and take, well, do you know what I can also do? I can get the 1 here while I'm at it. I can divide both of these rows by 2. So I'm going to do 1/2 of row 2 and 1/2 of row 3. Actually, let me color code this. Let's do this in orange so it looks a bit different. Okay, so 1/2 of 0, 1/2 of -2, 1/2 of 2, augment 1/2 of 0. Then 1/2 of 0, 1/2 of 0, 1/2 of 2, and 1/2 of 2. Row 1 is still 1, 1, -1, 1. Okay, so what do we get? We get 1, 0, 0, then 1, oh shoot, it should have been -1/2, oops, -1/2, to get that to be +1. Sorry about that. So now +1, 0, then -1, -1, 1, augment 1, 0, 1. Okay, hopefully I did that okay. Okay, so my next step is to get a 0 here, so to that end, let's do row 1 minus row 2. So let me write it this way. Row 1 minus row 2. So we'll have 1 minus 0. We'll have 1 minus 1. We'll have -1 minus a -1, so +1. We will have 1 minus 0. And everything else stays the same. Come on. Namely, 0, 0 for the first column, 1, 0, -1, 1, and 0, 1. So what this gives us then will be 1, 0, 0, 0, 1, 0, 0, -1, 1, augment 1, 0, 1. So the only thing I'm left to zero out at this point is this guy right here, because the one above it is already 0. So all I need to do to that end is row 2. If I add row 3, that'll get me where I want to go. So to row 2, I'm adding row 3. So 0 plus 0, 1 plus 0, -1 plus 1, augment, come on, augment, 0 plus 1. And the other two rows stay the same. Okay, so the other two rows are 1, 0, 0, 1, 0, 0, 1, 1. Okay, so finally, what do I get? I get 1, 0, 0, 0, 1, 0, 0, 0, 1, augment, 1, 1, 1. Okay, so this must be the same as 1 times x is equal to 1, 1 times y is equal to 1, and 1 times z is equal to 1. So the point where these three planes intersect is 1, 1, 1 in a three-dimensional space. Okay, whew, we did it. Let's do one more for third time's a charm, and then I'll let you guys go, I believe. Did I let you guys go? Yeah, I think I'll stop at this one. Okay, so let's do 6x plus 5y is equal to 20, or 2x minus 3y is equal to 16. Okay, so the coefficients of x are 6 and 2, coefficients of y are 5 and negative 3, equal sign is my augment, and then 20 and 16. Okay, so if my goal is to get this to 1, and I divide by 6, I'll have fractions. But if I subtract 2, that's 4. If I subtract another 2, that's 2. If I subtract another 2, that's 0. So what I'm going to do is I'm going to try something intermediate. I'm going to say, let's do row 1. Maybe I'll do it in purple. Let's do row 1 minus 2 times row 2. So I'll get that 2 I was talking about. You'll see why I'm going to do this in a moment. So this will be 6 minus 2 times 2. It'll be 5 minus 2 times negative 3. Augment, then it'll be 20 minus 2 times 16. Okay, so we get 2, negative 3, and 16. Okay, so what does that give us? That gives us 2 and 2. 5 plus 6 is 11, and negative 3. Augment. 20 minus 32 is negative 12, and 16. Okay, so it doesn't look like, as it stands, I'm going to be able to get the 1 in that spot. But let's focus now. Maybe I can get at least the 0 here. Can I get the 0 there, if nothing else? Well, yeah, because if I say, okay, row 2 minus row 1, that should get me the 0 there, and maybe that'll help. Then maybe I could go back later and get that to be a 1 in that first spot. So 2 minus 2, negative 3 minus 11, augment, 16 minus a negative or plus 12. And row 1 is still 2, 11, negative 12. Okay, so what does this give us? This gives us 2 and 0, that's good, 11 and negative 14, augment, negative 12 and 28. So as it stands, I still can't get a 1 in that first spot. But can I get a 1 in the second place where I'd like a 1, which is right here? And it looks like I can. If I divide So a negative 1/14 of row 2. So I'm going to take and divide each entry in row 2 by a negative 14. So I have negative 1/14 times 0, negative 1/14 times negative 14, augment, negative 1/14 times 28. Okay, row 1 is still 2, 11, and negative 12. Okay, so what does that give us? That gives us 2 and 0, 11 and positive 1, augment, negative 12 and negative 2. Okay, well, I'm still not to the point where I can divide row 1 to get anything nice. However, pardon me, can I zero this guy out if I subtracted 11? But remember, I'm not allowed to subtract 11, right? So what I want to do is I want to do row 1. I'd like to subtract 11, but I'm not allowed, so maybe if I multiply 11 row 2, that has a 1 in the corresponding spot, I'll be set. So let's try that. So 2 minus 11 times 0, then 11 minus 11 times 1, augment, negative 12 minus 11 times negative 2, row 2 is just 0, 1, and negative 2. So what we get then is 2 and 0, 0 and 1, augment. So negative 12 plus 22. So what's 22 minus 12? I claim that it's 10. Negative 2. Now, finally, I believe I'm able to divide row 1 by 2, and I won't have any fractions. So I'm going to do 1/2 of row 1, and it won't leave me with terrible fractions, which I can't stand. So if I take 1/2 of row 1, this will give me 1/2 times 2, 1/2 times 0, augment, 1/2 times 10. So 0, 1, negative 2. Okay, so what do we get when all is said and done? We get 1, 0, 0, 1, augment, 5, and negative 2. So this translates to the system. One times x is equal to 5, and 1 times y is equal to negative 2. So I claim the point where these two meet is 5, negative 2. And there we are. I hope this made sense, and I'll see you in the next section.